Before we start learning about machine learning, there are a few concepts to be clarified. In this lecture, we will briefly discuss the concepts of data, information, and knowledge. Data is a recording of known facts about separate objects or events. It could be numbers, letters, strings, so forth. Information, on the other hand, can be defined as the semantics conveyed by the data. We have another level, which is knowledge. Knowledge is the fluid mix of a framed experience, values, contextual information, expert insight. In short, we can say that knowledge is the verified information. Then on the top, we have wisdom. And wisdom is the ability to increase effectiveness. So wisdom adds value which requires the mental function that we call it judgment. I'll give you an example. If let's have a data such as red, street, 2.0 might not be understandable. However, if we put it together and we say traffic light on the corner of Khalifa Street has turned red, has a meaning which can be considered as information. The traffic I'm driving towards has turned red is a context that indicates knowledge in this case, which is the verified information. So I better stop the car, in this case is the wisdom. As you can see from the figure here, past experience can be leveraged in future novelty and decision making. You can see here it points to future novelty. The figure also shows two important concepts: the context and understanding. For the context, the raw data collection can be the gathering of parts. The information in this case is the connection of the parts. Remember when we talk about, for example, red, signal, and then when we assemble it together, or we gather this part together, then we manage to have a sentence which is understandable. So we have also knowledge, which is the formation, in this case, of a whole, and wisdom, in this case, joining all these wholes together. As mentioned earlier, past experience or data can be leveraged to make predictions and more informed decision making. But remember, a huge amount of data should be collected and analyzed to achieve this goal. So let's ask ourselves a question: how the data is collected? If you remember when you visit banks, companies, hospitals, you notice significant amount of data is gathered every minute and every day. Just remember barcode scanning in shopping malls and customer lining up for that. CCTV cameras in airports, factories, companies, e-government, in which each one of us is using it for services. So there is no doubt we are rich in data, but certainly we are very poor in terms of information. So the data comprehension does not seem to match the data acquisition today, and therefore tools to keep up with the growth are desperately needed. We are all aware of the database management systems, and it's improved over the years. They are considered to be powerful database design and query tools. But of course, they lack data analysis and predictions too. Well, to leverage the past experience, we need to discover and extract knowledge from the databases. So knowledge discovery here refers to efficient process of searching through large volume of raw data. So in this case, we'd like to find useful information patterns. So the word efficient here means fast searching and extraction of patterns. So the patterns can be rules, models, and statements. Let me give you an example. In a shopping mall or a supermarket, the data analyst can find that customers who purchase X are 98% likely to purchase, for example, bread. So what would you do if you are the supermarket manager in this case? I know you guess it right. This can be treated as a rule, and that's why we always notice changes in the way items are displayed in malls and supermarkets. A pattern can also be represented as a model. Let's have an example. If you would like to estimate the amount of insurance premium for a new customer. Also, it can be statements, such as customers who have an income, let's say between 20,000 and 40,000 UAE dirham, and own a house are safe to approve their credit card application. So why? Because if we look at our historical data, if we look at our records, we may find, for example, 100% or 99% of our customers, previous customers, who have a salary between 20 and 40,000 and have their own house, they usually pay back. And this will give us a confidence to approve new applications. Hello and welcome back to this lecture. In this lecture, we will define machine learning and discuss how is it different from data mining. We will also discuss the types of machine learning. Here we define both data mining and machine learning. We'll also discuss how the two approaches differ. So the data mining is a subset of business analytics. In short, we can say that data mining is the process of discovering patterns in the data. However, we have to note that learning algorithms are needed to detect this kind of patterns. So the more the pattern extracted are strong, the better the prediction will be. But let me tell you, most of the patterns extracted are not often interesting. Why? Because the data itself may have issues such as missing entries or errors. And we will deal with data preparation and data pre-processing in later stages in this course. Now, let's define machine learning. So machine learning, on the other hand, it's a subset of artificial intelligence. With machine learning, computers analyze large data sets and then learn patterns that will help to make predictions about new or maybe novel data sets. So machine learning is all about teaching computers to learn a bit like humans do. How we achieve that? By interpreting information and learning from our success and failures. For example, Netflix recommends certain movie to watch. How that is achieved is based on viewing preferences of other customers or other users with similar profiles. Another example is real-time fraud detection on credit card transactions. And of course, we'll discuss many examples throughout this course. Hello and welcome. In this lecture, we will discuss machine learning history and applications. Machine learning has three main types. The first is supervised learning. In this case, the training data is labeled with the correct answers. For example, spam, not spam, fraud, not fraud, pass, fail. The two most common types of supervised learning are classification. In this case, the outcomes are discrete labels, like as we mentioned in spam filtering. It could be regression, where the outcomes in this case are real values. The second type is unsupervised learning. And in this case, we are given a collection of unlabeled data which we wish to analyze and discover patterns within. So the two most important examples are dimension reduction and clustering. Finally, the third type is reinforcement learning. And in this type, an agent, which could be a robot or controller, seeks to learn the optimal actions to take. This is based on outcomes of past actions. In this course, we'll be discussing in details how supervised and unsupervised learning works. As you know, nowadays everyone is talking about artificial intelligence, or AI. But let me ask you a question. How old do you think the artificial intelligence field is? I know you figured out the answer. As you might know, researchers were talking about neural network in the 80s. As you can see in the figure here, the left hand side of the figure, you can see in 1980s era, researchers were talking about neural network. A neural network is the foundation of the revolution of the deep learning we witness today, in the right hand side of the figure. But what makes the field took all this time to be useful? The answer to this question will be revealed in the preceding slides. The limitation of computational resources was the main reason AI and machine learning did not progress as expected. As you can see in the figure here, computers were big. You can see in the left hand side of the figure. Expensive, and importantly, very slow. You can also notice the significant improvement in processing. You could see here from 1956 to 1980 and from 1980 until 2017. So you can notice the significant improvement in processing and drop in cost between 1980, for example, and 2017 in terms of price. There is no doubt machine learning dream grows through the years. With the advancement in computational resources, particularly because of the booming in the video game industry, AI and machine learning are becoming more affordable and useful. As you can see in the figure here, it took us 8,000 years just to move from the agricultural revolution to the industrial revolution. Another 120 years just to get our first light bulb. 90 years to land in the moon. 22 years more to invent the Wide Web. And finally, 9 years only to complete the Human Genome Project. The good news is, the computer technology is climbing dramatically by a power of 10, as you can see in the figure here. Although we are nowhere near what the human brain is capable of, many advanced and useful applications were developed over the years. Machine learning is currently applied to solve many problems. For example, machine learning can be used to discover financial and insurance frauds, investment risk, and credit history analysis. It can also be used to cluster customers based on sales analysis. It can be used for diagnosis of diseases. and the analysis of the effects of new drugs. It can also be used for city resource planning, national and local government policy making. The field is also successful to detect faults in product lines, identify an area that is highly classified for military and intelligence purposes, and can also be used to profile criminals, identify criminals and terrorists, detect money laundering activities. In this course and in the preceding chapters, you will learn how to develop such machine learning solutions. Although machine learning techniques are extremely promising, there are many challenges to be addressed first. One of these challenges is the data size. So the data size can be very large, in gigabyte or even terabyte. So if you think of it, you may reach the stage that whenever you build a machine learning model or you would like to train it, you will end up having a memory issue. The data itself may be built for different purposes, not for automatic learning. How often you find a data with some attributes that do not make any sense? Some entries that are not even managed in the way that it will be used for learning in the future. For example, you find instead of a gender, somebody may write F for female, somebody may write M for male, somebody may spell it out as male and female, somebody may write it wrong, somebody may write it even in a different language. Another issue is the data dimensionality is often high. It is common to have data with hundreds or even thousands of variables. The attributes are often heterogeneous and consist of a mixture of numbers, string, and pictures. How many times you look at a form, an entry form, and you find they ask you to put your name, your gender, your salary, maybe bank account, date of birth, and upload your image. If we want to get a way to describe this person, then we have to deal with all this different kind of or mixture of entries. Another way or another challenge is dealing with unstructured and semi-structured data such as web pages or audio files or spatial image or video clips. It's a difficult challenge. Why? Because what kind of attributes can I extract? And what kind of machine learning techniques can help me to extract valuable features? Because in order to use any of the machine learning classifier, for example, you need to have variables and attributes in the first place. So how can I get attributes out of image or a video? Moreover, we have another challenge. Most of the machine learning models are built on static data. But in reality, the data is dynamic. So you build a model today, and the data is changed tomorrow and needs an update for the model as well. Another important issue is the data quality, because garbage in, garbage out. So if your data is not clean, if your data is not accurate, do not expect a good model. Finally, the data value can also be sparse, and you need perhaps to normalize it before you use it in your learning system. Hello and welcome. So far we defined machine learning and understood its potential. In this lecture, we will introduce the machine learning algorithms. By now, We understand that machine learning techniques are important for acquiring structural descriptions from examples. The structural descriptions explicitly represent patterns, which can be used to predict outcomes in new or novel situations. The structural descriptions can also be used to explain how prediction is derived, and this is very important benefit. To understand structural descriptions, we need to answer the following questions. What is meant by structural patterns? How do you describe them? What form does the input take? To answer these questions, let's look at the weather problem example here. This is a simple data set you can see in the figure in here. And it's a typical data challenge. The purpose here is to detect whether someone will play tennis or not given some weather conditions. For example, if the outlook is sunny, temperature is hot, the humidity is high, no wind, then the person shouldn't play. Another person might be in the case of outlook is outcast, the temperature is hot, the humidity is high, and no wind, but this guy plays tennis. So in this case, if you look at the last column here, this is basically the class, or we call it category. This is a labeled column describing whether this person here, given this condition, play or not. And this is a kind of supervised learning. So this is a historical data in which learning model can be developed to extract valuable patterns here. And the purpose is when we develop a model here, we train a system to learn from these examples, then we can predict the class of unknown or unseen data. So in this case, we know our class. What we have here is attribute. In this case, we have 4 attributes. Sometimes we call them predictors, sometimes they call them features. We also have examples or instances. The instances independent examples of a concept. So each row here is describing somebody and their weather conditions, or whether this person is gonna play tennis or not. So the idea here is to use this data in order to create a classification model. So once we have unseen case, we can simply compare this case to our model and we can get the decision. Somebody may think, what's the model all about? The model is simply a summary of rules, as you can see in the right hand side. So for example, when you look at this data, we can finalize a pattern like this. If outlook is sunny and humidity is high, then the decision is not to play. Let's check it out. Outlook is sunny, humidity is high, the decision is no. Sunny, high, no. Sunny, high, no. But if you look at the example here, sunny, normal, then the decision is play. Similarly, in this case. So that means if somebody would like to play a tennis and you can ask this guy, is the outlook is sunny? And he says yes. Is it the humidity is high? He says yes. Then straight away you can say do not play. This is what the history telling us. So in another situation, for example, we can find whenever outlook is overcast, it's always the decision is to play. Overcast, play, overcast, play. Similarly in these two cases. So that means If somebody would like to play a tennis and ask a machine or somebody, can I play tennis? What's the outlook? Is it overcast? He says yes. Go ahead and play. Why? Because 100% of the cases we have, in the case of outcast, the decision is always play. Let's have another example here. The data can also be numerical. So in this case, the pattern can be if outlook is sunny, the humidity is greater than, let's say, 83, then the decision here is not to play. So if you look at the data, you can identify these three cases here. So the three examples, first, second, and third, you can see here the temperature is 85, 80, and 72. The cases all are sunny, which is very important because it's written here in the pattern, the outlook is sunny. Let's look at the humidity, which is very important because the humidity in all these cases is greater than 83. So that's why the decision is no. Here we can compare the classification rules and the association rules. It is easy to notice that classification always looks for correlations between the attributes and the class. You could see here, when we talk about outlook is sunny, humidity, for example, is high, the decision is no. So you can see here, we look for correlation between these attributes here and the overall class. However, the association rules always look to find association between the attributes themselves. Look in here, for example. If the temperature is cool, the humidity is always normal. And of course, you can verify this kind of patterns. If windy is false, that means no wind, and the decision is no, then outlook is always sunny and the humidity is high, for example. In this example, you can see we introduce the decision tree. A decision tree is a flow chart like structure in which each internal node represents a test on an attribute. For example, whether a coin flip comes up heads or tails. Each branch, in this case, represents the outcome of the test, and each leaf represents a class or a label, which is a decision taken after computing all attributes. So here you can notice all the patterns extracted are represented in the decision tree. Let's verify that. If you look at the first pattern, whenever the outlook is overcast, the decision is always yes. So this is the decision, which is the leaf in here. Right? Another pattern, if the outlook is sunny, we cannot decide whether the decision will be to play or not. We need another evidence. And in this case, we can look at the humidity. And if it's high, then the decision this time will be no. Otherwise, will be yes. So if the outlook is sunny, the humidity, let's say, is normal, the decision is always yes. If the outlook is rainy and the wind, there is a wind, which is true, the decision is always no. So in a case, we have a novel data or a case that somebody just come and ask us whether to play or not, we can ask about these attributes here, and then we can straight away know the decision. Why? Because we get a summary of all patterns here as rules extracted from the historical data we have. And this representation or a model can be used for future predictions. Hello and welcome. In this lecture, we will discuss the concept of generalization in machine learning. Generalization is a very important concept in machine learning. In order to develop some intuition about the concept of generalization, look at the figure in your right hand side here. Let's assume that each dot in this figure represents a news. The two colors have the following meanings. The blue dots here represent fake news, and the orange dots represent not fake news, or let's say legitimate news. So would it be possible to imagine a good linear model which can separate fake from not fake news? Let's try. If you have a line in here, then again you're gonna miss this point, and this point. Won't be classified accurately. If you try it this way, you're gonna miss many of the blue and one of the orange. So the simple answer to that is no. Well, it is possible to come up with a certain machine learning model which can separate fake from non-fake news, as you can see in the figure here. But you have to note that this model produces a very low loss, which is very good. However, we may face another issue here. Can you guess what this issue would be? When we added new data points to the model. For example, we added this data point here, this data point, and this data point. Unfortunately, the three added data points are in the wrong side of the classes. For example, the blue ones should be in this side, the orange one should be in this side. This is a clear case of overfitting. And by overfitting, we mean the model gets low loss during training but does a very poor job predicting new data. If the model fits the current samples very well, how can we guarantee that it will make good predictions on new data? As you can see, overfitting is caused by making a model more complex than necessary. So the goal of machine learning always is to accurately predict new data drawn from true probability distribution. Unfortunately, the model can't see the whole truth. The model can only sample from the training data set. So there are fields such as statistical learning theory and computational learning theory, and they develop statistical descriptions of a model's ability to generalize to new data. This is based on some factors, such as complexity of the model, the model's performance on training data. So a machine learning model aims to make a good predictions, as we know, on new or previously unseen data. But if you are willing, or if you are building a model from your data set, how would it be possible to work on unseen data? Well, one way is to divide your data set into two subsets. So we can have training data set, which is a subset to train the model, and a testing data set, which is a subset to test the model. So good performance in this case on the testing data set is a useful indicator of a good performance on the new data in general. Hello and welcome again. In this lecture, we will give you an overview of the Weka toolbox, which will be used throughout this course. We're going to use it to extract useful features from the data, perform pre-processing, and also develop and test machine learning models. The Weka Environment for Knowledge Analysis, Weka, was developed at University of Waikato in Hamilton, in New Zealand. Please Google it, download it, and install it in your computer. The link is provided also in this slide. Details and step-by-step installation process and other overviews of Weka are provided in the 3 lab sessions. Finally, these are additional resources to provide you with a general overview of some of the key machine learning applications. Please feel free to explore and learn more about this exciting field.